Okay, you're going to be doing some quantification. I don't know, is that a word? You're going to be doing some problems today that are going to be quantitative, meaning we're going to use some numbers. Okay, so I'm going to walk you through a couple of examples. We're going to do the second case. I'm not going to do the first one. I'll let you guys try that after I do the second case for this tension. Okay, so as we look here, we have this spherical object, and it is being held up by two ropes, not one. The first situation has one. This one has two. So we're going to draw a force diagram. I'm going to use a box for this one because it's going to be a little easier to do the box. It's going to have the gravitational force going straight down, and it's going to have these two tension forces going up. So I'm going to label them tension 1 and tension 2. They are at the same angles, so they have to be equal to each other. They have to each be supporting an equal amount of the gravitational force that is acting on this sphere. Okay, I said I'm going to give you an equation for the gravitational force, so let's do that. Okay, you will be looking at a lab next week that deals with the gravitational force and what we call weight, but you need this equation to solve these problems today, so we're going to go ahead and give it to you. All right, the gravitational force is equal to mass times the gravitational field strength. So M, again, I mentioned this in a previous video, is mass. We measure it in kilograms. G is what we call the gravitational field strength. And that gravitational field strength on Earth is equal to about 10. It's not exactly 10. It varies on how close you are to the surface of the Earth and the center of the Earth or sea level, or how far away from the center of Earth or sea level you are. The further away you get from the center of the Earth, the lower the gravitational field strength is. But we're going to take the average of about 10, and that field strength is measured in the units of newtons per kilogram, or newtons each kilogram, okay? So that's the value we are going to use to calculate the gravitational force acting on objects. So going back to our first problem here, I'm going to go ahead and write the equation for the gravitational force down here. Now we are only dealing with vertical forces, so I'm only going to do the vertical forces in my table. This is suspended. It is not accelerating. So it has a net force, or sum of the forces, equal to 0. It also has sum of the forces equal to everything going up minus everything going down. So I can now set everything going up minus everything going down equal to 0. So I see that my tension in the left string, or my tension 1, plus my tension 2 must be equal to the gravitational force, because I can add this to both sides to get the 0 out of there. We said that these are equal to each other, so I can rewrite that as 2 times the tension is equal to my gravitational force. I can plug my equation in for my gravitational force. So the tension in each string is the gravitational force divided by 2. Well, we have numbers for that now, so I can plug in my mass, which is 5 kilograms, times my gravitational field strength, which is 10. Divide that by 2, and I find that the tension in each string is going to be equal to 25 newtons. Because my total downward force here is equal to 5 times 10, or 50 newtons. And I said each string up here is going to be half of that. They have to support the equal amounts of weight. So they're each going to be equal to half of the gravitational force that's going down. All right, let's look at another one. Let's see. We're not going to do that one. Let me find the next one on our list. Okay, we're going to analyze this situation of the man pulling the 50 kilogram box at constant speed. So we know the mass of the box is 50 kilograms. They gave us the angle of 30 degrees. And they told us the size of this tension force here, which is going to be 200 newtons. So we will be looking at that in a minute. I know that that's a tension because it's a pulling force. And it has a rope there attached to the box. All right, so our force diagram for the box is going to have the gravitational force, of course, going straight down because this box is on Earth. It has a tension force going at an angle. The box is on a surface, so it must have a normal force. The other way I can determine if it has a normal force is if it is floating up in the air or falling down, it would not have a normal force. This box is doing neither floating in the air nor falling down, so it must have a normal force. All right, if I wasn't sure about friction, I could come over here. We need to do a separate force diagram to analyze component forces and do our X and Y axis. So I am going to do that over here. All right, so we draw in our X and Y axis. The Y axis is always perpendicular to the surface. The X axis is always parallel to the surface. And I can see that my angle is going to be right here. That's my theta. So I can see that my tension force has a horizontal component going to the left and a vertical component going up. Well, this is at constant speed. That means the sum of the forces have to be equal to 0. It means my forces have to be balanced in both the vertical or up and down direction and the horizontal or the left and right direction, which means I must have some force here counteracting that horizontal piece of the tension. So it's a frictional force. My motion is to the left, so my frictional force is to the right. Okay, then they ask us to solve for some pieces of information. So first they want us to write the equation for all the forces and components of force on the box in the vertical direction. So I have to know whether it's a Newton's first law or a Newton's second law. They told us constant velocity, which means Newton's first law, so they must add up to 0. And then it is everything on or parallel to my y-axis. So on or parallel to my x-axis. Everything going up is added together. That's my vertical component, which is the opposite side. So I can write an equation for that vertical component. I did not mean to put a sum there. It's the opposite side, so it's going to be the hypotenuse, but the hypotenuse is the tension force, and that is going to be multiplied by the sine of the angle, because it is not the angle or the side touching the angle. So I have my tension force, again, which is the hypotenuse, times the sine of theta. Both of those are going up, so they are added together, minus the gravitational force. So I can write my normal force plus my component of the tension in the vertical direction minus the gravitational force is equal to 0. Remember the gravitational force? I just gave you an equation for that a moment ago. It's equal to the mass times the gravitational field strength. So I'm going to go ahead and put that in my equation to help me solve for the next part. Okay, now they want to know the size of the normal force. So I'm trying to get the normal force by itself. So I can add the equation for the gravitational force to both sides, minus the equation for the vertical component from both sides. And I get an equation where the normal force is by itself. And that equation is the gravitational force minus that vertical component of the tension. Well, this makes sense because the two pieces going up have to add together to equal the piece going down, because we know we have a balanced forces or Newton's first law situation. So to find the normal force, I would have to subtract that piece from the gravitational force. All right, let's throw in some numbers. We know that the mass of the box is 50 kilograms. We know the gravitational field strength on Earth is equal to 10 newtons per kilogram. This vertical component can be found by taking that 200 newtons of tension force times the sine of 30 degrees. I can plug all of my numbers into my calculator and get a value for my normal force. Whatever that number is, I'm going to let you plug it into your calculator. I need to follow it with the proper units, which are newtons, okay? That N after the number is newtons. That's what we measure force in, are newtons. All right, remember when you're calculating these that your calculator needs to be in degree mode. Okay, so check that mode, make sure you're in degree mode. All right, now we're doing the forces and force components in the horizontal direction. So again, it's everything on or parallel to the x-axis. We have a balanced forces or Newton's first law situation. So those forces must add up to 0. Everything to the right or whichever direction you want to make positive. So technically, our convention is usually to make the direction of motion positive. So let's go ahead and do that for this one so we can get in that habit. That means the horizontal component of the tension. I don't know why I keep writing the summation there. Well, that is the adjacent side to the angle. So I can write an equation for that component as my tension force times the cosine of the angle. Remember, the tension is your hypotenuse. I multiply that by the angle. So I'm going to go ahead and put that equation in here because it's more helpful than this one. So the tension times the cosine of theta minus the frictional force. So now I can combine these two together, and the Ft cosine of theta minus the frictional force is equal to 0. I can add the frictional force to both sides. So I find, I'm going to go ahead and write it down here, that Ft times the cosine of theta is equal to my frictional force. So I can now plug in numbers. 200 is the size of my tension times the cosine of 30 degrees. That is the side of my angle, or the degrees of my angle gives me my frictional force. I'll let you guys plug it in your calculators. Make sure your answer has units on it, and those units would be newtons. Okay, go ahead and try the rest of the practice problems in the packet. If you have questions, let me know. We will post an answer key with explanations to the problems probably sometime this weekend, but no later than Monday morning. All right, good luck and have a great day.